be presenting a review of the paper titled Factors That Affects the Technological Transition of Firms Toward the Industry 4.0 Technologies. The contents for today's presentation is as follows. Let's do introduction. Firms are more likely to diversify into new technologies when they have pre-existing technological capabilities. However, adopting Industry 4.0 technologies is not just about existing knowledge. Factors like technological relatedness, complexity, and government R&D support play crucial roles. Moreover, government interventions are particularly important in the early stages of technological revolution, helping firms overcome the risk and uncertainties of innovation. This research aims to address three key objectives: identify the characteristics of Industry 4.0 technologies and analyze their complexity. Second thing is investigate how technological readiness, complexity, and government R&D support influence firms' technological diversification. Last one is determine which types of firms are most likely to succeed in adopting these new technologies. Next section is literature review. First, let's talk about technological diversification. Firms' ability to diversify depends on several factors: their size, age, and R&D investment. And qualified factors like CEO expertise and collaboration within R&D teams. Large firms or with consistent R&D investments are generally better positioned to diversify into new technologies. Furthermore, R&D presence is a key determinant of success. Next, we have technological relatedness, which is critical factor in diversification success. The principle of relatedness suggests that firms are more likely to diversify into technologies closely aligned with their existing portfolios. For example, firms with experience in cloud computing are better positioned to adopt cybersecurity technologies because of their shared technical foundation. However, traditional methods like cosine similarity, often used to measure relatedness, fail to fully capture firm level difference, highlighting the need for more nonsense approaches. The third factor is technological complexity. Complexity refers to the sophistication and variety of technology. More complex technologies often require advanced capabilities and significant resources, giving firms with strong knowledge bases a competitive advantage. Finally, let's discuss the role of government R&D support. Private firms tend to underinvest in R&D because of its characteristic as a public good. As a result, government intervention is essential during the early stage of technological revolutions, where risks are very high. Now let's move on to the data section. This study used a comprehensive data set to analyze how firms transition into Industry 4.0 technologies. Let me first explain the three data sources used in this study. First one is PateStat. This data set contains detailed patent information, including CPC codes, filing dates, and applicants. It helped measure technological relatedness and diversification patterns. Second one is case value. This data provides firm-level details such as size, age, revenue, profit margin, and R&D expenditure. Last one is government support data. This data identifies firms that receive direct R&D funding from government programs. Next, let's discuss the key variable derived from this data. First one is technological relatedness. This measures the similarity between a firm's existing technology portfolio and industry for all technologies, and it is calculated based on the co-occurrence of CPS code within patent filings. Second thing is technological complexity. The method of reflection is used to assess complexity based on the distribution of CPC code. Last one is government support. This is a binary variable where 1 indicates a firm received R&D funding and 0 indicated otherwise. First, let's discuss how technological relatedness is measured. It is calculated based on the co-occurrence of specific code in patent filings. First equation shows the probability of one technology being used when the other is present. Higher proximity value indicated strong connections between the two technologies. And the second equation aggregates the proximity of all related technologies in the firm's portfolio. Firms with higher relatedness densities are more likely to diversify successfully. Firms with higher relatedness are expected to have an easier transition into new technologies. Next, we have technological complexity. Complexity reflects the sophistication and variety of technologies. The studies used the method of reflection to measure complexity, which involves iteratively analyzing the connection between firms and technologies. Case of F, N is complexity of firm F. Case of T, N is complexity of firm T. M's of F, T is binary matrix indicating whether firm F is associated with technology T. Technologies with higher complexity values are more specialized and harder to adopt. The study develops a multivariate profit model to analyze the determinants of technological diversification. Dependent variable is indicating whether firm I entered technology alpha at time t plus 2. And the dependent variable is relatedness density of the firm. Complexity of the target technology binary variable for government R&D support, and firm-specific characteristics such as size and R&D spending and industry-specific controls like competition levels. Finally, let's look at the analytics methods used to refine the model. First one is box cost transformation applied to normalize data and stabilize variance for more reliable results. Second one is fixed effects which control for year-specific and industry-specific factors to isolate the effects of technological relatedness, complexity, and government support. Last one is subgroup analysis, separately analyzed firms with high and low technological relatedness to examine how government support interact with these factors. Now let's move on to the research section. First, let's look at the technology space. Figure 1 shows 10 IFO, Industrial 4.0, technologies positions in the technology space of Korean manufacturing firms. Large nodes such as quantum computers, cloud computing, and cybersecurity represent technologies with a higher number of patents. Figure 2b illustrates lightness among IFO technologies. Cloud computing and cybersecurity shows the highest proximity, indicating shared capabilities among firms. Another notable cluster includes augmented reality, system integration, and autonomous robots, highlighting overlapping technological requirements. This section analyzed the complexity and patenting trends of Industry 4.0 technologies over 3 periods: 2007 to 2010, 2011 to 2014, and 2015 to 2018. Figure 6 x-axis shows total number of patents representing the volume of innovation for each technology, and y-axis shows average ranking of complexity. Autonomous vehicles maintain positions in the known ubiquitous regions with high complexity, indicates limited competition and significant entry barriers in this field. Quantum computer shows consistent patent counts over the period. This stability suggests that the technology is in a steady developmental phase without significant competition. Let's first look at Table 1, which shows the correlation between variables. Technological relatedness is positively correlated with the dependent variable, indicating its strong role in enabling diversification. Technology complexity shows a weaker correlation with diversification, suggesting that firms face challenge with adopting highly complex technologies. Government support is positively correlated, reflecting its effectiveness in encouraging firms to diversify into new technology. Firm-specific variables like age, number of employees, and debt ratio also show significant correlations, emphasizing their influence on diversification capacity. Table 2 represents the regression results. Technological relatedness has a highly significant positive coefficient across all models, showing that firms with higher relatedness are more likely to diversify, suggesting that the alignment with existing technologies reduce barriers to entry. Technological complexity is smaller and sometimes negative, indicating that higher complexity makes diversification more difficult. Government support exhibits a strong positive impact, especially for firms with low lateness. This section highlights technology-specific insights from the regression analysis. Firms with medium-high technological stock benefit the most from government supports. As shown in column 4, the coefficient for government supports is positive and highly significant. This indicated that firms with substantial but not excessive technological resources are in the best position to leverage public funding for diversification. Low-density firms use government support to enter new technology. In column 8, government support has a strong positive impact for low-density firms. This demonstrates the crucial role of public funding in enabling these firms to jump into IFO technology that they would otherwise find difficult to adopt. To wrap up, this study provides important implications and acknowledges key limitations. It shows government R&D funding plays a crucial role in helping firms with low technological readiness adopt IFO technologies, and this support enables firms to overcome barrier and diversify into new advanced technology domains. However, the research has a limitation that they need additional study without manufacturing farms, and government support is only treated as a binary variable. Thank you for presenting.